Okay, you can.
It's my pleasure to introduce Shouhei Honda, who will be giving a talk on the topological stability theorem from non-smooth to smooth spaces with Ricci curvature bounded from below. So, thank you very much for giving this talk.
Thank you very much for introduction. First of all, I'd like to express my deep appreciation to for giving me this opportunity. Okay, so let's start my talk. The title of this one. So let's start. So I'd like to explain what is the meaning of the topological stability. Okay. What is the meaning of the topological stability? The meaning I will explain is as follows. The setting is this. Okay. I use many colors. Okay. Setting is this. We fix a convergent sequence of compact metric space. Okay. So this is a compact metric space. Then I should clarify the meaning of the convergence. Okay. Then in my talk, I adapt the meaning as a Gromov-Hausdorff convergence. Okay. This is a Gromov-Hausdorff convergence. And the second one is some curvature restriction. Okay. Okay, I will explain what is the meaning of curvature restriction. And third, this is a non-collapsing condition. Okay. So this is a setting. Then the conclusion of the topological stability theorem is this. Xi is homeomorphic to a limit space. Right? So this is a homeo. For any sufficiently large I. Okay. So this is the meaning of topological stability. Okay. So this is the topological stability. This is a statement is this. Okay. Okay, so next maybe it is better to give an example. There is a very famous example, okay, which is due to Perelman. This is due to Perelman. Okay. The statement is this. Sorry. Setting is, as I say, this is a compact metric space. And the second is curvature restriction. Okay. What is the meaning of this? This is a sectional curvature is bounded to below by a definite constant k. Right? In a synthetic sense. It's okay. What is the meaning of the synthetic sense? Well, this is a so-called Alexandrov space. Right? It's okay. And third condition is this. The dimension of xi coincides with the limit. Okay. And it is finite. Okay. Then The conclusion is this. Xi is homeomorphic to the limit. Is okay. So this is a very famous theorem of Perelman, so-called Perelman's stability theorem. Right. And moreover, Perelman states this homeomorphism can be improved by Lipschitz without proof, right? So maybe it is very hard to attack this, right? Because the Perelman wrote the proof of the geometrization conjecture, but he says this is a hard problem, right? But yeah, he thinks this is correct.
Can I ask a question?
Yes.
So how do you define the dimension of the limit space?
Okay, very good question. Okay, we have several meaning of the dimension, but they are same. The one of them is the Hausdorff dimension. It's okay.
Oh, okay.
Right. Okay, in the Alexander geometry, under the assumption of the finite dimensionality of topological dimension or topological Lebesgue covering dimension, okay, then the Hausdorff dimension is finite, and of course, then the topological dimension is finite. Then they are same. Okay.
Mm-hmm.
So this is a very good question. Okay. So this is a famous theorem of Perelman. Okay. Then let us discuss in the case of Ricci curvature. Okay, Ricci curvature. Due to this is a Chiga coding.
Oh, and just to be clear, so in the general version, you say condition 3 is some kind of non-collapsing, and here it's just dimension is non-collapsing.
Yes, right. Yes. So this is okay. Usually, in the theory of convergence theory, Riemannian manifold, we usually we have some notion of the dimension, and moreover, we can prove the lower semi-continuity of the dimension. Right. Right. Therefore, the non-collapsing makes sense. If the dimension coincides with the limit, it's okay. The plus the Phillips jig. Okay. The setting is this. The first one is the same. This is a compact. Second one is different. This is a Ricci curvature is bounded below by some k. Okay. In a synthetic sense. It's okay. Okay, then this condition is so-called now RCD. So-called RCD. RCD K and N. Right, like this. It's okay. And moreover, this is a non-collapse. It's okay. Well, this is a non-collapse. Okay. But the key point is this: we non-collapsed had two meanings. Okay. One of them is for sequence. Okay. Another one is a single space. Right? We assume both. Okay. In RC theory, okay, we usually say, okay.
What's non-collapsed for a single space then? Sorry, I don't quite understand the distinction.
Yeah, this is a very good question.
I apologize.
Yes. Wait. Let me explain. Okay, let us use a blue. Okay. XDN RCDKN is then is set to be non-collapsed if M is equal to the Hausdorff measure. Right? Yes. This is important because in the RCD theory, we can choose arbitrary measure. Right? So there is ambiguity of the measure, but the non-collapsed assumption is strict. So namely, the reference measure coincides with the optimal Hausdorff. Right? Yes. So this is good. So this is the definition. Right? Okay. Then we can okay. So this is the standard meaning. Okay. The dimension means the Hausdorff dimension. But in the for general RCD space, so we have maybe two meanings of the dimension. One of them is the Hausdorff dimension. Okay. Another one is a rectifiable, or sometimes called the essential dimension. Okay. So this dimension is determined by the dimension of the tangent space. So usually our essential dimension is at most Hausdorff dimension. But at the last year, there an example found by Wang. Okay, they state that there is an example such that Hausdorff dimension is not equal to the essential dimension. So, but in the non-collapsed case, all notion of the dimension coincide. So we have no confusion if we discuss the non-collapsed spaces. It's okay. Okay. Then the conclusion is this. Conclusion. Xi is homeomorphic to X for any larger. It's okay, but we need to assume the following. Okay, if X has no singular point, it's okay. And moreover, this assumption is essential. Okay, if we drop this condition, then there is a counterexample, even in the case of Einstein. So there is for example, yes, okay.
What is meant by singular point here?
What the singular point means okay, good point. Good. Okay. Yeah, I will write down the proof. I will write down the definition of the singular point. Okay, P is n-dimensional regular point. Okay, if any tangent cone at P is equal to Rn. Right. Well, this is the definition. Then the complement of the regular points, of course, this is a singular point. Okay. And moreover, this is equivalent to, well, there is an okay, this condition is equivalent to this one. So this is a reference measure is equal to 1. Okay. Maybe everybody can understand the meaning of what is the meaning of this. Right?
So for instance, Iguchi-Hansen metrics.
Yes, exactly.
Going to a point. Okay, that's
exactly.
That's why you need this extra thing.
Exactly. So for example, the Iguchi-Hansen metric on the tangent bundle of S2 that converges to the cone over RP3 under blow down, right? Yes. But the expansion metric is a non-compact space, right? Non-compact space. If we consider non-compact space, we can easily find such a counterexample. Because, for example, the simple example is this. Okay, we consider this is a R2, right? R2. And moreover, we consider we consider the point. This is the origin. And moreover, we consider some mountain like this. Right? Okay. Then, okay, this distance is I. Okay, I is an integer. Then I converges to 0. No, I converges to the infinity. Then this space converges to Euclidean space in the sense of pointed Gromov-Hausdorff convergence, right? Okay, but if we consider the handle like this, okay, then this is a topologically not homeomorphic to Euclidean one. Right? Therefore, it's easy to find a counterexample in the non-compact case. But in connection with Eguchi Hanson, okay, the one of the counterexample of this conclusion, that if we drop this one, okay, it can be found in the hyperkähler metric on K3 surface. Right? Okay. Yes. Okay, here is a remark. In the last theorem, okay, if the sequence xi and the limit space are smooth, okay, they're both smooth, then the conclusion can be improved to diffeomorphism. Okay. Yes. Maybe this is maybe you can easily expect this result, but okay. But we cannot this is important, write down such homeomorphism or diffeomorphism explicitly. Yes, this is just the existence, right? Is okay. Okay, so let's go to the okay, I will introduce a recent result about proved by Wang Zhao. Wait,
sorry, I'm not
Zhao.
sure if I understand your last point here. So where does the diffeomorphism come from? Is it from some surgery theory or something, or what?
No, not surgery theory. Yes, this is a some limiting behavior. Okay, this is based on some limiting behavior. Yes, so this is so-called Reifenberg method. Okay. Reifenberg method. Well, this is very famous in geometric measure theory. Okay, the classical Reichenbach method states for Hausdorff distance. But Chiga Colding generalized Reichenbach method to the intrinsic distance, that is the Gromov-Hausdorff distance. Right. Okay, roughly speaking, okay, well, this is a naive idea. Okay, we consider this for x and y. Okay, they both are no singular points. Okay, then this is epsilon cross. Okay, epsilon cross means in the sense of Gromov-Hausdorff sense. Right? Then, roughly speaking, the Reichenbach method, as a first step, we construct some open manifold x epsilon. No, x epsilon is a closed manifold, which is approximate to x. And this is y epsilon. And moreover, y the epsilon over 2 and something, so we can construct some approximate sequence of a manifold. Right? This is some x to epsilon, blah, 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 blah. So this is just a sequence. Right? The first step of the Reichenbach method is to construct an approximate sequence of a manifold by using a Gromov-Hausdorff distance with some modification of the Then if x and y are smooth, okay, then this argument stop at the finite time, because if epsilon is if this number is very small, okay, if this number is very small, then this is injectivity. This number is smaller than injectivity radius. Then in the after a finite step of this Reichenbach method, then the original manifold appeared. This is manifold appear. Okay, but by the construction of the Reichenbach method, this is a diffeomorphic. Okay. This is the first step. It's easy to diffeomorphism. Okay, but after the finite step, then by checking the carefully the construction, then after final step, then the original manifold appeared. Therefore, we can get a diffeomorphism. But if we consider the non-smooth case, then we need to take a limiting procedure. So this is a very delicate part. Yes, maybe I think it is better not to explain it the detail. Yes, because this is very complicated. Okay.
Okay, thank you.
Okay, thanks. Okay, so next, it is better to explain a recent result by Wang Zhao. This is a setting. Setting is this. They consider a sequence of closed Riemannian manifold converges to a sphere. It's okay. Converges to a sphere. And Ricci curvature of the manifold is bounded below by n-1. Then the conclusion is this. Okay, there exists Fy. This is a smooth map from a manifold to the limit. And moreover, this is a so-called normalized eigenmap. Okay. Such that Fy gives, so Fy is a diffeomorphism. Okay, diffeomorphism. Okay, and moreover, this estimate holds. Sorry. Yes. Okay, I'd like to explain what is the meaning of this estimate. The important point is this. The first one is this. This is almost one Lipschitz. Right? Almost one Lipschitz. Yes, this is a key point. And moreover, this is a by Helder estimate, right? By Helder estimate. Okay. In general, this point, this exponent cannot be improved to 1, right? In general. So in this sense, this diffeomorphism result is sharp. Okay. Moreover, this is a very explicit map. Okay.
Maybe you're going to come to it, but can you, so tell me if that's true, but where does that epsilon, is there like an intuition where that epsilon comes from?
Epsilon I comes from, epsilon I is depends only on, well, this is just the existence of epsilon I, but also we can state this one, we can state this statement by quantitative way. So quantitative way means, so, okay, I will write down, okay, this is the same. Okay, maybe it is better. This is the same result. Okay, 1 Zhao. Okay, the statement is this. Okay, if manifold satisfies Gromov-Hausdorff close to epsilon, and Ricci curvature is bounded below by n-1. Okay, then, but epsilon is very small, right? Epsilon is small. The smallness depends only on the dimension. Okay, then there exists, no, sorry, a diffeomorphism, but this is a normalized eigenmap such that this is a diffeo, and 1 minus psi dzxy 1 plus psi and dfx fy 1 plus psi, sorry. Okay. What is the meaning of the psi? Okay, psi is a standard notation in Riemannian convergence theory. Right? Where psi means psi epsilon n. Right? This means that this is a constant, which is a very small constant, depending only on epsilon and n. Right? But if n is fixed and epsilon is very small, then this value is very small. Right? This is a quantitative, but this is equivalent by contradiction argument based on the compactness of the Gromov-Hausdorff convergence. Is okay? Yes. It's okay? Yes. This is a theorem. Okay, so we are now in a position to introduce our main result of my talk. Here's the theorem. So this is a joint work with my student, Yuanlin Peng. The setting is this. Okay, Xi is a compact manifold, but the limit space is smooth. Okay. Smooth closed manifold. So this is a compact metric space. But the limit space is closed. Okay. Closed. And second one is Ricci curvature is Xi is bounded below by some k. Okay, in a synthetic sense. And we assume right? This is a non-collapsed assumption. Then the conclusion is this. There exists Fi, a map. This is a map Fi from Xi to the manifold. This is a canonical map, but associated with an isometric embedding. Right. One key point is this. We fix an isometric embedding from the limit space to a Euclidean space. Okay. If we consider a sphere, okay, then there, of course, there is a canonical one. Right. The canonical map is an eigenmap. Right. Each coordinate function is a first positive eigenfunction. Right. This is eigenmap. Such that. Okay, then the conclusion is Fi is a homeomorphism. Okay. And moreover, and this estimate hold. This is the same. Yes. Okay. So previously, based on the Reifenberg method, as I explained, this Lipschitz part, Lipschitz continuity of the map is unknown. Okay, this is the conclusion. Okay. Okay,
So
here is the lemma.
I want just to make sure I understand maybe what you're about to say about this theorem. In the previous Wang Zhao theorem, this eigenmap.
Yes.
Does this come from the first eigenfunctions of the Laplacian?
Exactly. Because under the Gromov-Hausdorff convergence, then any eigenfunction converges to the limit uniformly. Yes, this is the key point. This is so-called spectral convergence.
Right. Okay.
Right. Therefore, so in the limit case, if the limit is sphere, then of course the isometric embedding can be realized by eigenmap, right, over the first positive eigenvalue. Therefore, by using the the first, the first, okay, so I will explain. Maybe it is better. Okay, this is how to obtain this one. So we first take, this is a phi n plus 1. This is a first, this is a eigenvalue lambda 1. Counted with multiplicity. Lambda 0 is a constant. This is 0. Okay. Lambda 1 is a non-trivial. Okay, then lambda n plus 1. This is this is n plus 1. Sorry. Eigenvalue. Right. So phi n plus 1 is a corresponding eigenfunction. Okay. Then we consider the map like this. Phi 1 blah 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 phi n plus 1. Okay. But this is the target is Rn plus 1. Right. So we need to normalize. Okay. The normalization is this. This is just a norm of this. Right. Right. What is it? This is a norm of this one. Right. Maybe this is a very standard. Right.
Okay, I see.
It's okay. Thanks. Okay, here is a remark. The first one is if the sequence is also smooth, okay, then Fy can be chosen as diffuse. Okay. And moreover, if Xi has a singular point, then Fy is not by Lipschitz. It's okay. So if we consider the rugby ball means the rugby ball like this. It's okay. This is a two-dimensional rugby ball. This is very thin. Okay, but we next like a bit fat rugby ball. Okay, then we consider a little more fat one. Okay, then this converges to sphere. Okay, well, this is a very typical example. Okay, in this case, Fy cannot be bi-Lipschitz. This direction, this is Lipschitz. It's okay. But the another direction, this one, this is not bi-Lipschitz, not Lipschitz. It's okay. So if you wish, then I will be able to explain why later. Okay. And moreover, if the limit on phi can be chosen, can be, it's okay, can be chosen as an eigenmap. Okay, so this is related to the classical theorem due to Takahashi. Takahashi theorem states that if the manifold can be isometrically embedded to a Euclidean space with the same eigenvalue, then this is a minimal immersion into the sphere. Yes. Then Fy can be chosen as is a normalized eigenmap. Okay, so this is a part I explained. What is the meaning of due to spectral convergence? spectral convergence means all information of the eigenvalue and the eigenfunction are converged to the limit. Okay, this is equivalent to the convergence of the heat flow. Well, this is a key point in the development of the recent development of RC cells. Okay.
Wait, so you're saying
finally,
that the recent development is to focus on the heat flow as opposed to think about the individual eigenfunction?
Exactly. So the previously, the Chiga coding proves that the spectral convergence only for eigenfunction. Then for sequence of manifold. Okay, then we can prove that the convergence of the heat flow. So this is the story of the Chiga coding. But in the RCD setting, okay, then in RCD setting, the Giglio-Mondino, Savare proved, they proved the convergence of the heat flow. Okay. What is the meaning of HTI denotes the heat flow on xi, right? But the HTF denotes the heat flow on the limit space. And FY means converges to the F in L2 sense. Okay, this makes sense. Okay, the L2 strong convergence or H1 to strong convergence, LP convergence makes sense for measured Gromov-Hausdorff convergence sequence. Okay, then if the sequence converges to the limit one in L2 strong sense, then their heat flow converges to the limit one. So this is the convergence of the heat flow. Okay, if we establish the heat flow, the convergence of heat flow, then we can get the spectral convergence as a corollary. Moreover, we can prove the some convergence of the Laplacian. Okay, this is a key point in the recent development of the RCD. For instance, the local harmonic function converges to the limit one. So limit one is also harmonic and something. Okay. This is so related to the splitting theorem in RCD theory. It's okay. Okay, let me explain how to prove. Okay, so this is the red color. Okay, this is the red color. Sketch of the proof. Okay. The first one is the step. Maybe I think that this proof is very standard, but previously there are no tools to prove the map constructed later is actually homeomorphism. Yes. The map is very natural. The step one. The first step one, the find phi. This is denoted by phi 1, blah, 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 phi n. Sum Rn. This is isometric. This is by Nash embedding. Okay, the existence of isometric embedding, such an isometric embedding, is guaranteed by Nash. Right? And the key point, the second one is step 2. Okay, find an approximation. Phi I j such that phi ij converges to phi I. Okay. But I should clarify the meaning of the convergence of this one. Right. So the convergence of this one means, sorry. Okay, means the first one is the phi ij converges to phi I uniformly. Uniform. This makes sense. Okay, this makes sense. And moreover, H1 to strong. Okay, H1 to strong means the energy converges to the limit one. Okay. So we usually lower semi-continuity of the energy. Okay. Under this. But the H1 to strong convergence is assumed the energy converges to the limit. Okay. So there is no loss of the energy. So this is the important point. Okay, this is the first one and the second one. So this is an explanation of the second one. And the third one is Laplacian is also equi-Lipschitz. Okay, Laplacian, yeah, in the sense of the Dirichlet form theory. Okay, this makes sense. Okay, this is just a L2 function. But we assume this is also equi-Lipschitz. Moreover, this is uniform. And H1 to strong. So they are very strong convergence, right? But we can easily find such a way, such one. So this is the meaning of the convergence of phi ij to phi I. Okay, how to find of this one? This is by solving a Poisson equation. Poisson equation. Okay. So under assuming the lower bound of Ricci curvature, there much regularity theory of the Poisson equation. Okay, so roughly speaking, if the Laplacian of f is L infinity, then f is Lipschitz, for example. Right. Yes. So yes.
So these are constructed by solving the same kind of Poisson equation that the phi.
Yes. Okay. Exactly. So roughly
speaking, and then all these extra properties they somehow come from this theory of the.
Yes. Exactly. So we first consider this, right? This one. Then we take the approximate sequence of this one, right? Okay. And of course, phi I is smooth, right? Okay. Therefore, the Laplacian of phi I, it is smooth. In particular, Lipschitz. Okay. Therefore, we can find the equi-Lipschitz convergent sequence of this one. Then psi I is a very good function. This is a Lipschitz function. Okay. Then we can find a phi I like this. Like this. Okay. So because of the Poincare inequality. If we get a Poincare inequality, then we can always find phi I. Okay. And moreover, psi I is a very good function. Therefore, by the regularity theory of the Poisson equation, then phi I is very good, which means a Lipschitz function. Therefore, we can realize this. Okay. Okay, but in order to prove that phi I converges actually to the phi, sorry, no, psi I. Okay, so this is a misleading. Okay, I will rewrote. This is a phi I. It's okay. Then, sorry, this is misleading. Okay, this. Okay, then we find phi ij by under assuming like this. Okay, so this is a direct consequence of the Poincare inequality. Okay, there is a unique. Okay, then we can find a convergence to some function phi tilde I. Okay. But we need to prove phi tilde I actually equal to phi I. Okay. In order to prove this coincidence, we need the convergence of the heat flow. Right. It is equivalent to the spectral convergence. So if we establish a kind of the heat convergence of the heat flow in another context, convergence context, then the similar story will work. Okay, so this is the second step. Okay. I forget the numbering. Okay, so this is 14. Okay, so next is 15. The next one 60. Okay, this is a step 3. This is a very natural map. Okay. We consider this is a embedded space into a Rn. Right? It's okay. So this is a phi m. Okay. Then we consider the projection. It's okay. This is a projection. Okay. Along the exponential map from the image of phi. Okay, this is well defined. Okay, this is smooth. Okay, then let. Okay, therefore this is a pi, and define fy to mn by this convolution. Okay. What is the meaning of phi I? Well, phi I means this is approximate sequence. Phi 1 I, phi 2 I, blah blah blah, phi ny, right? It's okay. Because this converges to the phi 1. Okay, so this converges to, of course, to phi 2. Okay. Therefore, the image of this phi I is very close to the image of this one, like this. It's okay. Okay, this is a fy. Sorry. This is a phi I. Sorry. Phi I xi. It's okay. The image of phi I of xi is very close to the image of phi because of the uniform convergence. Right. Therefore, we can take the projection. Okay. So I think that everybody understands this map is very natural. Right? Maybe everybody, maybe if we look this statement, then everybody try to prove this map is actually homeomorphism or not. Right? But previously there is no tool to prove this one. Okay. Okay, maybe this is almost final step. Step 4. Using a heat flow smoothing and Bohner inequality, then we can get inequality. Oh, sorry, this. Well, this is not so hard part. Right. Okay. This is due to a recent work. We can follow an argument by blue neighbor Seymour. Okay. But the hard part is this. Step 4, 5. Applying blow up and transformation theorem and stability of Laplacian. So this is stability of Laplacian is, roughly speaking, it is a consequence of the convergence of the heat flow. Stability of Laplacian implies we get lower estimate. So this is a very new technique, okay, which is developed by recently. So for example, transformation theorem, this is developed by Chiga Jam Neighbor. Okay. And the final step. Invariance domain. Implies Fy is homeomorphism. It's okay because okay, as I say, that by using a Chiga calling result, Xi is actually topological manifold. Yes, by using actually topological manifold because the limit space is smooth. Because so there are no singular point. That's the previous result by Chiga calling yields the Xi is homeomorphic to a manifold. And moreover, this estimate yields the image of of course, the image of the Fy is closed. But invariance domain implies image of Fy is open. Therefore, this is a surjective. This is a homeomorphism. Okay, now it is better to finish my talk. Thank you very much for your kind attention.
Yeah, thank you very much.
Thanks.
That's wonderful.
No, not wonderful.
So I guess, yeah, I open it to the audience for questions.
Yeah, no, yeah, this is, thank you so much for staying up so late to give this talk to just a few of us. But, this is, it's really very nice experience, and, the sort of talk that makes me feel, very good to do math. And I learned a lot, and this is, the best kind of talk. Thank you. You explained everything so clearly.
Yeah, definitely. Appreciate it.
What about this this last point here? Invariance of domains. What is that?
This one.
I'm not sure if I understand.
This one. Okay.
Yeah.
Invariance of domain states this. So if we this is a statement for manifold, right? Topological manifold, right? So Mn is a topological manifold. It's okay. And we consider the same dimension, Nn. Okay. And we consider a map F. Okay. This is a continuous. It's okay, continuous. And F is injective. Sorry, just a moment. F is injective. Okay. So this is the assumption of the invariance domain. Okay. Then the conclusion is this. Then Fmn, the image of F is open. This is this is done by applying the result of the homology. Yes. So this is the result in topology. Yes.
Oh, okay, I see.
Yes.
I had a kind of question. I think you may have answered it right at the end, but I wanted to see what was essential about having a smooth limit manifold.
Okay,
obviously, you shouldn't be able to expect Lipschitz, any form of Lipschitz, because. But is there anything else that goes wrong, or can you degrade your distant estimate and still conclude a homeomorphism or something?
Okay, that's a good point. Okay, maybe the one key point okay, the key point is this. The key point for the smoothness of the limit is this picture, this one. Okay, this is smooth, and moreover, this map is C11. Okay, this is a key point. Okay, in the proof of this one, then okay, this is a okay. Let me explain. This is a normalization. Normalization. Okay, under this normalization, we need to check the each coordinate function is included in the domain of the Laplacian. Okay. So roughly speaking, okay, I will write it. Okay. Roughly speaking, the phi is included in the domain of the Laplacian if and only if there exists psi. This is L2. Okay, such that of course this is just this makes sense. Phi, I forgot is psi f for any f. This is H1. It's okay. This is just a definition of the Laplacian. Okay, but so under the composition of the projection, we need if psi. Sorry, the psi is not a good one. This is the first one. This is the we next to the phi is the psi, the delta. And f is r. This is a function f. This is a C11. Okay, if we call it C11. Okay, then this map is also this one. Okay. In order to get a kind of this one, this property, we need a regularity of the map F. Okay, this is appeared in the projection. Okay, if we consider the singular spaces, which can be embedded to isometrically in some sense into a Euclidean space, but in this case, I don't know how to get such a regularization of this projection. So this is a key point when we use the smoothness.
Yeah, and you would definitely have to lose regularity because you couldn't conclude that you can't conclude one Lipschitz in the other direction because then you'd have a contradiction.
Exactly.
So there must be some, interesting.
Okay. And moreover, maybe I think it is better to explain more. Okay, if we consider this, okay, this is okay. Let me explain. Okay, this is a map. Okay, this is a function. Okay, this is a singular space. Okay, singular space. But if we assume this is a L infinity is a sum C. Okay, this is a bound. Then under this rescaling, under this rescaling, no, maybe it is better to not to write the measure. So this is a rescaled space. Okay, and this is converges to a sum space. So this is some pointed Gromov-Hausdorff sense. Dy. Okay, and we consider that under this rescaling, we usually rescale the function as follows. This is a minus sum C. No, it's okay. So maybe it is better to write more precisely. Is okay. Okay, let us consider this station. This station is so-called tangent space. Right? If we fix a point x, okay, if we fix a point x, then we consider this rescale. we consider R to 0. Then after passing to a subsequence, this sequence always converges to a some metric space in the sense of pointed measured Gromov-Hausdorff sense. Okay, then we want to discuss the convergence of the function and after rescaling. The correct rescaling is this. One. Okay, under this rescaling, the Lipschitz constant does not change. Therefore, this converges to some function f0 something. Right? So this is a function on the limit space. The key point is this. Okay, why we want to prove a condition like this? Okay, then the key point is this. If we get this one, then under the blow up, this situation is so-called blow up. Okay, then the limit function is always harmonic. Always harmonic. Because under this scaling, this is the rescaled Laplacian. Okay, this Laplacian is defined on the rescaled space. Okay, then we consider the rescaled function. Okay, then by definition, we can easily get this is this. Okay, this is okay. If of course this is bounded, then this is very small number. Under this convergence, this value is very small. Okay. Therefore we can apply the stability of the Sobolev function, then we can easily expect the limit function is harmonic. Right. Then the harmonic function plays a key role to analyze the tangent space. Because for example, any tangent cone at a point is a metric cone, for example. Metric cone. And metric on the metric cone, any Lipschitz harmonic function is a splitting factor. Is a splitting factor. So this is the so-called splitting theorem. Right. Therefore, if the limit function f0 is non-trivial, then f0 coincides with the splitting factor. Okay. Then the limit space is split of R times sum Z. Okay. This is the key point.
Thank you.
Yes, thanks.
I had a question in a sort of a different direction. So this is sort of a silly maybe.